Okay, so I have a kind of non-explanation, which is that that's because of how if you take a tensor product of two, of two state vectors or two sets of state vectors, that ends up being how the thing lays out. It ends up laying out in this kind of space filling curve sense.
Okay, but that's when you take some kind of, I don't remember which one, Kronecker product or the other product, where you're literally just taking, okay, so that's interesting. So you're taking two things and you're outer producting them. I mean, you start off with two dimensions that are independent, but now you're weaving them together. And our convention for dealing with matrices, what is the ijth element? So you've got two products. You've got the thing with the indices. You've got a Aij, Bkl, if I'm not mistaken, right? And you're trying to make some product of those things, which is just a C X, AB or something, right? Okay, so how do you do it?
So I'm going to get I will certainly get indices backwards and things, but you're basically saying CAB hang on, let's get this right.
Well, is it effectively one of these array contract operations, which is essentially just laying out? How do you lay out? Can you show me how you lay these things out? So you're laying them out. You've got a rank 4 tensor, which is the outer product of those two tensors. Those two. Right. Okay. So now to get go ahead.
You can then flatten.
Literally flatten in the usual Wolfram language sense of flattening.
Right.
I mean, it's some kind of operation where you're okay. So that's the operation you're doing now. What the hell is that operation? And what is that operation from a mathy point of view? You don't want that. You want some operation for the outer. You want an operation for the outer. You can't just say outer. You want to say outer list or something. 500,000 elements? Okay.
Whereas if I do that, that will presumably get me back to.
Is the Kronecker product the thing that you've done?
Yeah, right. I mean, well, that's the thing I've inverted here, right? So I started with the tensor product basis.
Yeah.
And take these. That will give the same result as up here. That's what the partial trace is undoing.
Okay. What is that operation in terms of just tensor indices, the partial trace?
It's just tracing out by one index. So you're just averaging out over a single index.
Okay. Okay. I'm still thinking here. So essentially, this Kronecker product thing is what's going to lead to that weird space filling behavior.
Right, right. And so right now, I agree, I don't have a particularly good physical argument for why that happens. All I can say is, tensor products describe the Hilbert space of a composite quantum system is a tensor product.
By tensor product, we mean Kronecker product.
Well, the Kronecker product is the special case of the tensor product for rank 2 tensors.
Okay,
right.
But like in von Neumann's formalism for quantum mechanics.
Yes. The tensor product is just a generalization of the Kronecker product for arbitrary rank.
I need to remind myself what the Kronecker product is relative to outer. What is the Kronecker product relative to outer?
If I recall outer correctly, it's the same, I think, isn't it? Assuming outer is actually taking an outer product.
It is.
Yeah. So if you take an outer product, Okay. What would be called an outer product of vectors in the case of matrices is called a Kronecker product. So the outer product is strictly speaking the rank 1 case. The Kronecker product is the rank 2 case, and the tensor product is the arbitrary rank case.
No. Look at the documentation for Kronecker product. The very last line says there's an array flatten done for the Kronecker product. Kronecker product is the array flatten of the outer times.
Right.
So it's the array flatten of the outer times. So the outer times would be for rank 2 objects would be a rank 4 object, right?
Right, but like in conventional terminology, the outer times would be for rank 1 objects and would return a rank 2 object.
Yes, but whatever. But I mean, the generalized Kronecker product can perfectly well just does that last thing there.
Mm-hmm.
Okay, so you're saying that in Hilbert space, that the way quantum mechanics works, the formalism of quantum mechanics works, it is doing that.
Yep.
And what Tally and Max were saying is they're looking at the outer product before it has been Kroneckerized, before it's been array flattened, and they're saying, look, it's just a Gaussian, basically.
Something like that, yeah.
Right. So the nub of their objection is, why are you doing this flattening? Why are you doing this weird flattening operation that is the Kronecker product?
Right. Why aren't you just looking at outer?
Right. Okay. So I think then you have to, you push that problem back to old Johnny, so to speak.
Right.
And ask how that works in the formalism, in the von Neumann formalism. I don't know the answer. I mean, in other words, in the normal formalism, why are you doing a Kronecker product of this thing rather than an outer product? Well, because you are trying to get it, trying to map it onto a Hilbert space of the same dimension, if I'm not mistaken.
Not the same dimension, but crucially, you want your operators to have the same arity. Right.
Okay.
The dimension of the Hilbert space on which the Kronecker product acts is still the product of the dimensions of the Hilbert spaces that are inside the product.
Fair enough.
But the crucial point is you end up with a tensor of the same rank.
Okay.
So if you start from, matrices, if you start from rank 2 linear operators, you end up with rank 2 linear operators. You don't get some weird operator in the product space that you don't know how to deal with.
No, I understand, which is, okay, arity, yeah, you're taking tensor rank, or
yes,
is what you mean, right. So exactly. So the thing, look, you started, okay, the weird point is you start from 2 photons, which have their own world of degrees of freedom.
Mm-hmm.
And then you want the superposed state, which is acting like 1 photon in the sense that it has the degrees of freedom of 1 photon. Right, that's the basic point, right? And the question is, how do you achieve that? And the claim is that by a linear algebra sleight of hand, so to speak, in the early formalism of quantum mechanics, this is what is done. It's an array flatten. And you're just doing the same thing. Now, the question is, why is it an array flatten? And hopefully we can give a better answer now.
Right.
And I think the answer is because this is, what you're trying to do. Okay, let's explain again. You've got this this natural 2-dimensional space that comes from each photon has its own dimension, right? Rank 2 thingy, okay? But you are still trying to extract a single phase out of that.
Right.
And the question is, how do those dimensions come together to make that happen?
Mhm.
And the answer you are claiming is that you are crisscrossing across the, you're doing this thing where you're crisscrossing across the, uh, the higher dimensional space of possibilities. And what do we think the physics of that is? I mean, with respect to branchial space, you're imagining that there's this kind of geodesic coming down the multi-way system, and you're asking the question, what is the relative phase of geodesics that wind up at different places in the multi-way system, right? And your major claim is that you are going to map it so that the overall phase going from one side to the other is, let's say, minus pi to pi.
Mhm.
Although I think some people would say, the photon phase, every time there's a minimum to maximum, it goes through 2 pi.
Right.
But the main point is you're mapping this two-dimensional thing onto a one-dimensional phase parameter.
Mhm.
And I guess it doesn't really matter how many times it turns around, but the main point is, how do you get I mean, what you want, look, what you're trying to do, yes, this is kind of obvious, okay? Look, it's obvious, okay? It's got to be a space-filling curve because you want continuity from one local point in branchial space. You want the phase at a neighboring point to be similar.
Yep.
Right? Therefore, it has to be, it has no choice but to be a space-filling curve, basically. You can argue about which one, but it's got to be continuous with respect to small motions in branchial space. Yet it's going to wind up as a one-dimensional quantity. I think that's the argument, basically.
Mhm.
And you can probably re-coordinatize branchial space by taking a different, space-filling curve, but it doesn't really matter much. I mean, this will be a particular. Now, I mean, I don't know whether there may be some reparameterization that's possible, but that reparameterization is probably going to wind up being the phase of the photon is. I mean, there's probably an arbitrary gauge transformation basically that changes the phase of the photon.
Yep.
Okay, so let's walk through this one more time. So the basic point is you're doing Huygens principle in all possible ways. The result is a two-dimensional array of outcomes. But you must map that two-dimensional array of outcomes onto a one-dimensional coordinate system in branchial space.
Yep.
If you're going to do that and you require continuity, then that mapping has to be a space-filling curve.
Mhm.
And that's basically where this effect is going to come from.
Right.
Because that's going to mean that as you propagate down that space-filling curve, the distance that you go is, well, you're visiting different parts of that two-dimensional plane to cover the whole thing, which you have to do. And how would you do it? I mean, you could go in a spiral or something, but that's, I don't know what, I don't know. You have to argue for this particular space-filling curve probably, but the main point is that it's somewhat unsurprising that, okay, so the real reason this is happening is because your measurement process is picking up just this 1 degree of freedom thing, even though there are really two photons there, two superposed photons there.
Right.
And so now to close this loop, you have to be able to explain the measurement process, which means you have to do the Born rule thing,
Mm-hmm.
which I would claim is another thing you should look at.
Right. I have some minimal examples, but it requires more investigation.
This is getting there. This is very close. This is almost ground to my standards of grindingness. So let me just zoom out for a moment. I mean, the basic point here is the reason there is quantum interference is kind of the thing that we've been saying for a long time. That is that the GD6 in the multi-way graph get led. Yeah, the things that are what is the point? The things that are nearby in branch Hill space have small path weights. I mean, in this particular case, the path weights are just a diffusion pattern.
Mm-hmm.
So this somewhat surprising thing is that going across the screen at the back, that as you go across the screen, that you're scanning through branch Hill space, including going to the extremities of branch Hill space and back again, multiple times as you go across the screen.
Right.
Why? What is the real reason for that? The real reason is, well, hell, I mean, the real reason is because you've got a one-dimensional thing that you're trying to extract from a two-dimensional, I mean, in general, branch Hill space is infinite dimension. I mean, it's not, the multi-way graph, this particular case, we happen to be able to, I mean, look, one of the points here is that in this particular case, we happen to be able to get a convenient two-dimensional representation of the output,
mm-hmm.
which is purely coincidental,
right,
in a sense. And okay, so basic point is the mapping. Yeah, I mean, I think this is basically correct. And then now you got to get this Born rule thing. Is this your Born rule story?
Yeah. Sorry, I was just.
Yeah. Okay.
This is the minimal case of the Born rule, right? You have two branches, each with weight 1/2. If you then project one branch onto the other by doing a completion, so you're projecting the X branch onto the Y branch or the Y branch onto the X branch, the corresponding branches take a weight of 1/4, where previously they had 1/2.
You need to do a bigger example of this. I don't really get this. And I would do 3 branches. Can you do 3 branches?
I can, but that's going to get more complicated because.
Okay, well, do you have a different case here with 2/3?
I'm going to try a different case. Then it starts to matter what's projecting onto what. Let's see. I may have to run this for more than 2 steps. I forget how long it takes to actually achieve. Yeah, I probably have to run this for 3 steps. And did this give the right answer?
What is this supposed to be showing?
So what we should be seeing is, okay, we get 1/9 and 2/9. Yeah, that's right. Yeah, okay, so we started out with weights of 1/3, 2/3. If we project onto the Y's, we get 1/9. And if we project onto the X's, we get.
Why are we getting from that rather than 4/9?
Yeah, this is what we need to figure out. Why are we not getting 4/9? Let me see the states graph. It's a little bit easier to understand.
Well, it's only got, maybe try running for one more step.
Let's see what's going to happen. Hold up.
Well, this has to be figured out.
Mm-hmm.
I'm sorry, just pulling it back again for a second, okay? Basic. Right. Quantum interference is basically a phenomenon of observing in physical space that the point is that in the multi-way graph, everything is very simple. It only looks weird and quantum interferency when you're projecting into physical space by making essentially measurements. If you were sitting in the world of superpositions, nothing would look at all, there wouldn't be any interference phenomenon, so to speak.
Right.
The interference phenomenon is the result of doing that down projection in a sense, projecting down to measured states. I don't think it's going to save you.
No, but I realize why it's only showing 2/9, which is in fact the right answer, because this completion is projecting x onto y and y onto x.
Yes.
So you're multiplying 1/3 and 2/3, which gives you 2/9, which is correct. What you actually want is to project x onto itself, and I don't immediately know how to do that. So I tried the naive thing, but the naive thing doesn't work.
Hold on. X onto itself. So I don't know either. Yeah, I mean, 2 copies of the system seem like they're an obvious way to start. Maybe that's what you already did.
Right. No, I haven't tried that, but we should.
Anyway. Get the Born rule. You're on track here. But I would say tactically, you might want to look at what you wrote previously, see whether there are things you can obviously change that would clarify this, and then I would have a Q&A section at the end.
Yeah, I agree. Or maybe, I don't know. Should it be a Q&A section, or should I just release a sort of technical supplement?
I would have a Q&A section. I think it would be much more approachable.
Okay.
I mean, including, isn't this just a Gaussian in 2 dimensions? Yes, but it has a space-filling curve that's what measures it.
Right.
But it's measured along a space-filling curve, basically.
Uh-huh.
I mean, I think since you now know the objections, why not just do a Q&A to address them?
Yeah, I can.
I mean, in a sense, that's what we've done with the project as a whole by having that Q&A section, on the website.
Mm-hmm.
But I mean, now an interesting question is for Max to figure out how to do this with local multiway systems. I wonder what the analog of all this stuff is in local multiway systems.
Right.
It's going to be a little bit more complicated because he has to use graphs and things. Go ahead, what?
That's another thing for my project list is doing both finalizing the local multi-way code and doing some investigations with it.
I've now even forgotten what the global is. That the Dirac representation somehow?
Yeah, well, if our hand wavy picture of the Heisenberg and Schrödinger representations is right, then yeah, this is basically the Dirac representation, where each expression is a separate node, just like in a local multi-way system, but the events are total, and in particular have isomorphism testing, just like in a global multi-way system.
Yes, I see. Local events, local states, global events.
Exactly, yes. Which I think is an interesting picture that, at least for me, helped me understand local multi-way systems much better.
Yes. I mean, we still need to get multi-space figured out.
Uh-huh.
Um,
Yeah, these things.
let me look. Yeah, you should implement this. I mean, probably you should call it a global. I mean, that's not a local multi-way system. That's a
Yeah,
that's
but
a
this is a function I wrote, which I called local multi-way system, because this is back when I was trying to figure out what the hell local multi-way systems were really doing.
so I
And
would recommend that you rename this global multi-way system so that we don't get totally confused.
no, I agree. Yeah, yeah, because it's not a local multi-way system. But yeah, I mean, you can basically see what's happening. I mean, hang on, if I run the same thing with so that would be the associated global multi-way system.
So you shattered it into its constituent parts.
Exactly. Yeah. So you can see here, this event is producing two B's and an A. So you have these three edges.
I like this. You should make this into a. Can you just package this up into a function repository function?
Yeah. But there's a lot more stuff I want to. I mean, because right now this just works for strings. Well, actually, I did produce this prototype hypergraph implementation, but it needs some work.
Look, I don't care. Just for strings is already useful. I mean, the basic point is in the flow of this project, it's important to have things in. Look, if I write anything based on this, right, I'm going to want code that is going to continue to work.
Right. That's the thing that concerns me, because I have my general view is when I submit things to the function repository, I want that. I guess I guess it's the same philosophy you have for internal system functions. That when I submit to WFR, I want to be certain that the design is something I agree with and I'm prepared to defend.
Yeah, well, I agree that's. But I mean, in this case, what's the issue? Isn't it just the same as the multi-way system, but it just shatters everything into characters? So it needs basically a what am I saying?
The only reason I'm hedging is that it's unclear how general I want to make the code before I submit it. Like in an ideal world, I would want it to take the exact same the association specification as the global multi-way code, which right now it doesn't do. It just takes in strings.
Just submit this, because this part is going to still work, even when you make the general thing work as well.
Okay, I can do that.
Okay. Well, let's see. Can I come to my confusions? Okay, so maybe I can share my screen here. Okay, so I am fighting forward on the MetaMath stuff. Okay, and I mean I've got a bunch of different things. I've been fighting on the let's see what I've got here. By the way, I put that list of your projects into the Institute folder.
Okay.
Yeah, I think in terms of workflow, I want to get this MetaMath stuff sort of squared away. Once that is in reasonable shape, I suggest looking at the computational complexity business.
Yeah. And by the way, I mean, I've been a little bit I guess jealous maybe is the right word. There's a lot of interesting stuff going on with the metamath discussion right now, which I just wish I had more capacity to help with, right? I mean, like a lot of this, analyzing proof structures and curating axiom systems and making designs for axiom schemas and things like I feel like I might have
you do need to be part of that axiom schemas and so on.
Right, but I
mean, the good news is that we're getting some other people involved, and I'm sort of somewhat driving this, and yes, you should be involved. I mean, I've been avoiding involving you because I know you're busy with a bunch of other things.
Right. I mean, no, I appreciate that. I realize I'm I'm beginning to sound a little bit unreasonable.
No. It's. I mean, enthusiasm for all these things is good. Okay, so I can show you just all kinds of stuff here. There's lemma. Okay, so I think I'm at the point where I'm not totally freaked out about the notion of entailment versus equations versus whatever, but I'm going to try and write it down because I'm still a little bit confused.
Great. Okay. Oh, sorry. Completely. Xerxes just messaged me with a slightly urgent question. For the colloquium this week, do we want to try and get an external speaker? Xerxes wants to reach out to Alex, someone or another, some categorical quantum mechanics person.
I could volunteer to talk about. I really want to make sure we have a colloquium that people can actually understand this week.
Okay. Okay. I mean,
maybe I should talk about metamathematics because I think I can, even though I'm not really ready. I think at least I'll say something that people can understand.
Sounds good to me. I'll get back to Alexis.
I think that's the right thing to do. I mean, let's not have another incomprehensible, high mathematics one.
Right.
Then I think we should also have some of the junior folk will be ready to present some things.
Yeah. I mean, it sounded like everyone was saying, "Oh, yeah, maybe in a couple of weeks," but no one wants to do it yet.
Fine. Well, why don't you throw it at me then? I mean, it's going to be incredibly difficult for me to get this together by Thursday, but I'll do something. Let me know when you're.
Okay.
Okay. All right. So let me throw some things out there. So this is. I want to talk about what. I'm still struggling with what's the point. Okay. So what do I mean by that? So metamathematics, the way I view this is you were looking at cities on the Earth, and there is a certain intrinsic differential geometry associated with the surface of the Earth. And then there are particular cities that people live in. And there's a certain amount of information from the configuration of cities about the underlying differential geometry. And there's a certain amount of information that the differential geometry implies about the cities.
Yep.
The question is, how does the infrastructure of metamathematics relate to the reality of mathematics? Okay. Right. And we're starting to get better information about the reality of mathematics, both from Euclid and from this MetaMath project, and we'll probably ingest some other theorem collections. Mm-hmm. Okay, that's one thing. Then there's the question of, okay, so what are the things that go on in math? Okay, so we've got this kind of meta thing where we've got axioms and we've got lemmas, and the lemmas allow us to kind of speed up. So in this metamathematical space, our theorems of interest are dotted around, right? Mm-hmm. Hopefully we're going to have better data on just how they're dotted around. You know, I know that a little bit for basic logic, how they're dotted around, etc. Right? Somewhat unlike in physics, maybe not unlike quantum mechanics, I don't know. As soon as you travel a path, you can kind of reuse that travel by adding a lemma and thereby compress your mathematical space, or at least your perception of mathematical space.
Mm-hmm.
Now, what is the relationship? What should I think about as the relationship between a lemma and a completion? I mean, a lemma.
One type of lemma, right?
Well, it's only a lemma if these are two-way edges, unless you believe in branch equivalence, in which case it's always a lemma.
Right.
Right? So, in other words, the concept that branch equivalence implies lemmas, what the heck does that mean?
I mean, that's univalence, right?
I know that's univalence. I know. And that implies, what does that imply? If we look at the branchial space here, if I add a lemma, I'm basically tucking in. So I might have a particular foliation of this on which I have a particular branchial structure.
Mm-hmm.
If I add a lemma, I'm going to change that branchial structure.
Yep.
If I compress these two things to the same thing, I'm going to compress the branchial graph by merging two nodes.
Right. You're doing some kind of homeomorphic contraction.
Right.
Okay. Here's the kind of philosophical picture that I have for what's going on, which may or may not be correct, but I don't know. It's my current intuition. So I don't know if there's an essay by Tim Gowers about the two cultures of mathematics, which you may have heard of or read, in which he makes the distinction between kind of theory building and problem solving as the two kind of distinct activities that mathematicians do.
Yeah, which is similar to the thing that the Grothendieck quote and the Misha Gromov quote.
Yes, right. Yeah, right. I think probably multiple people have pointed this out. So theory building is basically a story of branchial expansion, right? And problem solving is basically a story of branchial contraction. Because in theory building, what you're interested in doing is building up as many possible lemmas as you can that could be used for shortening future proofs. But in problem solving, you're interested in taking lemmas that already exist and using them to kind of compress the branchial space down to find a particular proof of some result. And so the substitution lemmas, which are those are the things that go down kind of vertically in the proof graph. Those are increasing the expansion of branchial space. So the substitution lemmas are the things that are really underlying the theory building side. The critical pair lemmas, which are the things that collapse the branchial space that go horizontally, those are the things that are kind of crucial for the problem solving side.
Well, okay. So in terms of these pictures, what you're saying then, look here, okay, so to make a claim, okay, so this is the, Gowers, Grothendieck. Anybody not beginning with D? I mean G rather. You're another G. Okay. So this is the Gorhard, Gowers, Grothendieck, and Gromov theory.
Right.
G4 theory. Okay. So I mean the basic claim is okay. So theory building. versus problem solving.
Mhm.
Okay, so I would claim that theory building is, exploring mathematical space.
Right. In
And
other words, yeah, exactly. You want to maximize branchial extent.
right, but
Whereas
this one is finding specific geodesics.
in which you want to minimize branchial extent. Right.
Yes. Well, hold on a second. Let me just say this.
Because theory, and the reason being that in theory building, you want to build up as many lemmas as possible, right? As many substitution lemmas as possible. Because the more substitution lemmas you have, the more you can use them in future proofs to shorten things.
Sure.
The more mathematical technology you have. So in other words, you want to maximize the number of independent paths through the multi-way system that exist. And the way you can maximize that is by maximizing branchial expansion.
Well, or alternatively, I mean, I don't know where you're going with that. I mean, I just see that as being, in this case, you're collecting lemmas. You're going and exploring different things and collecting lemmas, which you
Yes,
can
right.
then use to contract to do all kinds of stuff here.
Yeah, that's my point. So each independent path yields a distinct substitution lemma. The
Sure.
maximization of substitution lemmas is therefore the maximization of branchial extent.
Wait a minute. You're not actually applying the substitution lemmas, are you?
No, you're maximizing the number of independent paths.
Right. Whereas in this case, once you've
Theory
applied
builders
a bunch of
don't
those
use the
lemmas,
theory.
what's that?
The theory builders don't use the theory. They just develop the theory. The problem solvers then use the theory.
Right. Okay, but let's look at this for a second. When you say, okay, so then there's the question of branch equivalence, which is basically saying, which is adding something which is not, branch equivalence is like a model, right? Adding branch equivalence to this is adding something that wasn't there to begin with. For a one-way multi-way system, branch equivalence is a model.
I don't like that.
Well, it's something. What is it?
I think it's a meta model, right? It's a property that models must satisfy.
Okay, fine.
It's a property you need in order to have models somehow. But it's not a specific model. It's not giving a semantic interpretation to anything.
Fair enough. Well,
Except
yes and no.
It's giving semantic interpretation to the branches, I guess.
Yeah.
In a weird way.
Right. But I mean, so this, to say that every branch is compressed, what will that do to this picture? How do I do it here?
How do you do a completion?
No, but I want to do all possible completions.
Yeah. Well, I mean, Knuth-Bendix completion will do that.
All right, show me how. Okay, so I've got this. And now
so if you get rid of the initial condition and the step number, and you just call canonical Knuth-Bendix completion. Actually, in that case, it'll give you nothing because this is a causal invariant rule. So that will just give you an empty list.
I see.
But
okay, if this was not causal invariant, then branch equivalence actually says something.
Right. But one thing you could do is take the whole multi-way system thing, including the initial condition and the step number, and then call Knuth-Bendix completion, which will kind of pretend that it's not causal invariant.
Okay, so that's taking every branch and debranchifying it, right? Is that right? Why doesn't it have an AA goes to ABBB here?
Because it's seeing that that's already resolved. It's only looking at the things that are currently unresolved as of the
I
fifth.
see.
So um, you could do a table. It's a little bit grotesque, but
Yeah, I understand. All right, so those are completions. And they force one step. They force everything into one step. So if I were to add these, it's going to make a total mess.
yep, afraid so. Wait, do you want append or do you want join?
That wasn't as much of a mess as I'd expected. Okay, what do I learn from this? The hell do I learn from this? I've got all those equivalences are now two-way equivalences, right?
Right.
Pulled up to their current step. Okay, all right, but so then, all right, this is fine, but I'm trying to understand. Okay, so imagine that I try to make models. Or maybe, were you finished with what you were saying, or was there more to the story?
No, that was pretty much it.
Okay, all right, okay, fine. Okay, so imagine you're making models. So I now have some model making technology, although I have not tried really using it here. Walk me through the story of foliations as models. So in this graph, what we're saying is ABB can go to ABA. Well, let's take AA, right? AA Well, okay, what does causal invariance mean for these things? Causal invariance means, does causal invariance mean that this is totally trivial in the end, in this case?
The what is totally trivial?
That every theorem is true?
No. No, definitely not. Right? AA goes to ABBB will never be syntactically provable in this system.
I see. Okay, fair enough.
No, I mean what causal invariance says is just that theorem proving is trivial.
Right.
It's that there's minimal algorithmic difficulty in proving theorems.
There are no wrong turns in theorem proving.
Right, exactly. If you apply every possible rule that can be applied, you can't go wrong.
Though it could take a while.
Sure, sure. But yeah, I mean, right, right. I mean, yeah, the computational complexity is unbounded, but the algorithmic complexity definitely is.
Right. What does that have to do with the curvature of the space, so to speak? That it can take a while to converge. It means that two geodesics that will ultimately end up at the same point, they may not be geodesics, who knows, are wandering far away and will eventually come back.
Right.
Okay, so here, the question is a BBBB provable from AA? Answer, not generically. But by picking a model, so one version of a model is this multiplication table thing. Making sense?
Yep.
So I don't understand how you make foliations from multiplication table.
Well, the multiplication table, I'm not completely sure I understand the question, right? The multiplication table defines a set of equivalences between words. A model defines a set of equivalences between words.
So the multiplication table, but the multiplication table is going to make a lot of these words identical.
Yes, it defines the maximal set of equivalences between words.
Fair enough.
An object with a multiplication table is the maximal distance away from the free object.
All right. But a less extreme model, one that adds some random lemma or random relation, not provable in the original system, right?
Right.
So in particular, in this case, we could add the lemma.
Well, any elements of an anti-chain. Right.
Right.
So a multiplication table case is the case in which every element of the anti-chain becomes comparable.
But wait a minute, there's many anti-chains here.
Right.
But it's every element of every anti-chain becomes comparable in the multiplication table.
Well, yeah, every pair of incomparable elements in the partial order should become comparable.
Yes. Okay. So let's take, in this example, let's take the relation ABBB. Okay, so this is now added. So now how do I read off? So here, the distance from the root, if I'm not mistaken, is the foliation that I've just defined here. Is that right?
Distance from the root.
This root here.
And what does it mean for a distance to be a foliation?
Well, I mean, it defines the slices in the foliation.
If you mean the level sets of that distance function define the slices of the foliation.
That's what I mean, yes.
Yeah, then, right, yeah, yes.
Does it have to be a two-way equivalence or not?
Not in this case, no.
When would it have to be?
If you had a two-way multi-way system.
Okay, so let's say I've got this then. Okay, so now this is these level sets. This has those level sets, right?
Mm-hmm.
Okay, so in this setup, I'm still confused. There's still a partial ordering here, and we're not just dealing with slices. Right? It's just that there are more things that are defined by the partial order than there were before, right?
Right, because you don't have a maximal, maximally non-free object.
But in a maximally non-free object, what would it look like? Would I be able to say?
It would be a total.
Yeah, it would just be a line.
Right, or it would be homeomorphic to a line.
Okay, if I have multiplication tables here, each one of these things is just going to give a value from the multiplication table, isn't it? So that means many of these things will just be equal to B or whatever else.
Yeah.
So many of them are just equal. I don't understand how they make an ordering. See what I'm saying? I mean, in other words, when I have the multiplication table, if I'm not mistaken, ABB is equal to element, is equal to whatever it is, A or something.
Yeah. So you add an equivalence relation between A and ABB.
Yes.
So what's the problem?
Well, but when I add that equivalence relation, I'll be adding an equivalence relation for every element here. So, with a multiplication table.
Why is that an issue? It's what you want.
I understand. Then every element is one step from the root. So I don't understand. I mean, the picture that we have of making these essentially slices, I don't understand the relation between that and this view of making models.
Mm-hmm.
Do you get what I'm saying? Because with this multiplication table, everything is one step from the root, isn't it?
Well, because it's a maximally non-free object.
Fine, but what's the interpretation? If we're thinking of this in terms of foliations of the kind we've done before.
Yeah.
Right? Your claim is that in this case, I could take this picture and I could reproject it back onto. So actually, this is what we need. This is what we need. I knew we needed something along these lines. Okay, so what we need is we need a way of saying apply this rule to foliate this other object. See what I'm saying? Foliate that's making sense. So in other words, what we're saying is foliating the second object with the first, we're saying that ABB, okay, now we put sort of a foliation line here, whoops, that goes under the AA and up above the ABBB, right? Am I wrong? I mean,
No.
okay. And so then we put a foliation line under the ABBB and coming down through there. What the hell is the relationship between these? I see. The foliation lines say what could be related. They don't necessarily say what is related, but they also say what can't be related by the things which are in the same level set, so to speak, with respect to these foliation lines. Am I right?
Yep.
Do you think we can make something that foliates? Do you think we can make something that does that? I mean, in other words, it shouldn't be that hard. What's that?
I thought I did.
Really? Where is it?
It's another one of these things on my code list, right? I mean, hang on. Yeah, there we go. Hang on. Can I share screen for a sec?
Yep.
This thing here that just takes in a specification of I want these things to precede these things which precede.
Okay. Can you send those to me in the chat so I can play with this?
Yeah, hang on. Let me dig up the code.
Well, it's in the CloudGet.
I actually modified the CloudGet a little bit.
Ah, okay. All right.
But yeah, I produced some things like that for my bulletin.
Well, here, why don't you send me the code and let me play with it? Okay, so this is saying in those sequences, what are those sequences? Those are saying what precedes what. So those are the new level set.
Right. So you can see, yeah, this is the first level set described by this thing here.
I'm not seeing. Well, I'm not seeing. Are you showing me something?
Yeah, am I not sharing?
No, you are sharing, but you just selected one cell.
I was trying to select this list.
I'm not seeing that selection.
Oh, okay, hang on. This is slightly weird. Hang on, let me try. Resharing.
Are you showing it on a different screen, maybe, or something? Oh no, no, your mouse is moving around. Your mouse was moving around there.
Oh wait, hang on. Maybe I was sharing. Now can you see this?
Yes. Yes,
okay.
I was seeing a completely different screen.
Yeah, okay, I was sharing the wrong screen. Sorry.
Yes. Okay.
Saying, this thing.
I want this. Can you send me this code, please? This would be super useful.
Yes. Okay. Hang on. Well, okay, I can send you the CloudGet version first. Interesting, like that. Right. Hello?
Yeah, yeah, I'm here.
Oh, yeah, I just want to check I hadn't disconnected.
No, no, no. Um, sorry. Yes. Did you send me? I need to go get my dinner in a minute. Are you able to continue in about like 20, 30 minutes or something?
Uh, Possibly. It depends how long this is going to last. I've been trying, perhaps foolishly, to get back into a more human sleep schedule.
Fair enough. Well, okay. I'd really like to. Um, I can. I'll tell you what. I'll just get food and I'll continue this conversation. Okay. Um, that I mean, we won't go too long. The
Okay. Oh
um,
yeah, but I mean, by the way, I should say that yeah, this foliation stuff is another thing that I want to WFRFI because I think it's going to be useful. But again, it requires some cleanup.
right. Well, let me put that on the list that we were making. Um, all right. Where did you send? Did you send an email? Did you send the thing in the chat?
I sent it in chat.
No, but that was just the CloudGet version. You were going to send me the more real version.
Oh yeah, sorry. Hang on, let me do that. Out.
Okay. You know what? I'll be back in just a couple of minutes. Okay.
No problem.
Okay, I'm back. Foliation.
Hey.
So could we make this into a proto WFR?
Yeah, I think so. It's just I'm not completely happy with the design, but yes, I think this could easily become.
Right here, let me just let's just do it, just so we know what we have.
Well, there are two things that are useful in different ways, right? That there's the code for making for making inertial foliations, and then there's this code for making arbitrary foliations. And I think it makes sense because they have different interfaces. I think it makes sense to have them as separate functions.
Yeah, I agree. All right, so let's just do this. Okay. So one of these would be multi-way foliation graphics. How far away to say it? Or is it not just multi-way? Is it multi-way systems or is it just graph foliation?
Strictly speaking, it would work on any DAG, although I've only been using it on multi-way systems.
Well, should we say post set?
Yeah, okay.
Okay. You know, the fact that I have this convention of copy pasting the name of the function to make the file name reveals a level of laziness in creating these things that's rather remarkable. Okay, so what we have to do is give the graph here. What are we? Where are we putting in the different things here? So the other one will be, what would we describe the other one as? The flat foliations one.
Poset inertial foliation graphics, or is that too much of a mouthful?
No, it's a complicated concept. We really want to say inertial foliation.
Would you rather flat or?
I was thinking flat, maybe.
Okay.
I mean, I think that inertial, in what sense? I mean, inertial is pretty weird in the case of quantum mechanics, for example.
Yeah, fair enough.
Okay. Which one is which? What do we do here?
Oh, so that's just the ordinary foliation graphics.
What do you mean?
That's not the flat foliation graphics.
Okay. Do you have that code? Can you send that to me just so we can put something in?
Have that.
Is there a good reason why this isn't broken into separate functions here?
Sorry, why what isn't broken up?
Oh, that. Like the cells. Okay, what does this take as an argument?
It takes the actual graph or the poset, and it takes the list of lists that corresponds to the foliation.
And what's all this stuff here? 0.1. What's that?
That's styling information.
Okay, but let's package that some other way. What are those 0.10 and so on doing?
So that's giving centering information.
In what sense?
So hang on, if I... So if you want to give a slight offset in each to each foliation line, either a vertical or horizontal offset, then you can specify that as the third argument. So that small gap, the small vertical gap you see there, is only because I've specified that offset.
Okay. Foliation offsets. Offsets. And foliation style. Okay, so now here, maybe we'll give a graph. And then we give slices. And that is going to be, okay, and then we have an options pattern there. And now we say, those two things were in a list, right? The directives and so on were in a list, right?
I don't believe so, no.
Oh. Oh, they were. What's that red?
That's the default styling.
Maybe that should be the default styling.
You mean the purple thing?
No, I'm not sure the purple should be the default. I think red should probably be the default.
Okay.
Okay. Now, let's just see if this actually works. Ta-da! Wow, why does that look so weird?
What did you do?
I just made it fewer steps. Let's try changing.
So actually, yeah, no, that looks okay, except for the
Yeah,
fact
it does. The what?
except for the fact that you don't have an offset. That actually looks correct. It's
Well, I
also,
thought I put in an offset. Look.
oh yeah, you have one. Okay, try. It may be a graph layout issue. It seems to work best with those kind of
I had digraph embeddings.
right.
Oh, for God's freaking sake, it just does, that's all it does. Oh, that is very weird. Can that possibly be right?
Try changing evolution graph to, sorry, try changing states graph to evolution graph, which is kind of a cheat. But oh yeah, okay. Then you have a different problem. Well, if you wanted to, you could try threading the. Yeah, this is going to get a little bit complicated, but you could thread the step number across the list.
Don't worry about it. Well, we'll debug this further. If we can specify for yarn how to debug this, we should. Okay, let's just look at the flat foliation, and then I want to look at something different because okay, so you're saying here, look, do we want the same options?
I believe so.
Line density horizontal, line density vertical. What's this? Tan horizontal. What are all these things?
Right. So yeah. So the line density, horizontal and vertical. That's essentially that's the thing from which you calculate these offsets. Then the tangent, horizontal, tangent, vertical. That's giving you effectively the beta parameter. If you were to think of this as a Lorentz boost.
Yeah. And what's the transform?
So the transform that should just be a hash. In the if you were putting this on as an epilogue to your graphics, that should just be a hash.
Just an identity.
Right.
But this is an epilogue here, but we actually want it to be. What's this vertex list? So that's a different thing.
Mm. Yeah, ignore the draw foliation lines.
I remove it from this file.
I believe so. Hang on, let me just check. It doesn't have any. I don't think anything depends on it. Yep. You can take it out.
Okay. Okay, now does this, how does this draw this? How does this one draw it?
What do you mean?
Well, to apply it to a graph, I just want to do a show, is that right?
In this case, yeah.
So,
But in the flat case, not.
no, I understand. So here, how does it know what the range of coordinates is for the graph?
Well, this is the point that in the flat case, it doesn't need to. In the flat case, it just takes the embedding and it just draws lines at some angle across it. Whereas the non-flat case requires actually knowing more information about the structure of the graph.
Okay. All right, so this is now, let's just do this. Okay, we've almost got this. Collation offsets. Okay, so this is now, I would argue the beta should come first. So why are there two beta parameters?
Because you can you can have hang on. Can I cook up an example that makes it clearer what's going on?
Is that tan beta or is it gamma?
It should be beta.
Does that work to have, I think, default density is 1. Okay. Okay. Oh, splatteroo. Oh, this thing was only the
Yeah, it needs to be an epilogue.
as opposed to a show.
Right.
Well, just the graphics of that. Really? I didn't even know graphs could have epilogues.
Mm-hmm.
Ah, what's the vertical and horizontal? How do I get rid of the vertical lines?
What were your defaults?
0, 0.
That shouldn't be happening. Can I see your defaults?
Yeah. Zero, zero. There.
Hang on. What's that? That 1 1. Change that to a 0 0.
Maybe I want that to be 0, 1. Oh. Well, I seem to want it to be 1, 0. Okay. So here, then, I would say, actually, I shouldn't need to do both of them, right? I should just be able to say, okay, I need to fix that. I'll do that. I'll do that later.
Right, but you only need to do 0.20, not 0.2, because you only have
I
one
know.
affiliation lines. Like I said, I really would like to redesign this code to make it more consistent. I didn't write this with the intention of having it be a general purpose thing.
Okay. It's not perfect, but it's something. Okay. So, all right. So then this gives us the ability to essentially make models to understand how to make in a model. This is saying things in lower slices can be proved from each other. Things in the same slice cannot. Right? That's the sort of defining feature. And right. So if you have two possible multiplication tables. So if you have one multiplication table, everything is defined. All right. So my question now, I don't want to keep it too long, but my question now is, okay, what are the causal edges? So we've got these models, and they, okay, what is that analog of general relativity? In other words, we can say we make a model. I mean, well, we're trying to make some coordinate system by building this model. Well, okay, first question is, what's the analog of, I mean, what does curvature mean here, for example?
I'm not sure that I understand. Didn't we? I thought we already discussed the significance of critical pairs and things like that, right?
Try it again.
What the significance of critical pairs?
In what respect? I mean, critical pairs. Go ahead. Give me your holonomy story. That's the story you were going to give. Yes.
Right, right. I mean, yeah. I mean, holonomy is the extent to which geometrical information about the direction of a vector fails to be preserved when it's parallel transported around a closed curve, right?
Yeah.
So, in other words, you have your vector, it's pointing in a particular direction in branchial space. You parallel transport it around some closed curve in the multiway system, it's no longer pointing in the same direction. The reason that happens is because you have branch pairs that aren't converging. Right? If all of your branch pairs converge, then any parallel transport you do around a closed curve will always perfectly preserve geometrical information.
Yeah, but so what here? What is the?
So your critical pairs are indicative of non-trivial holonomies.
Yeah, I understand, but so what? What do those mean in this case?
What do you mean, so what? I thought you asked about what curvature was.
Okay, but the curvature is reflected in the presence of branch pairs. Right, I understand that. But so then the question is then, what is the significance of curvature in this proof story? The answer is curvature is
the reason for there being algorithmic complexity in theorem provers.
Yeah, okay.
It's the reason why you can't just apply all possible rules and see what happens.
Well, okay, but branch pairs, these are unresolved branch pairs.
Right. Right.
But is that what curvature is in a standard causal graph? I'm very confused. If we look at a standard causal graph in space-time,
yep,
the basic claim is that the branch pair, the survival time of branch pairs determines curvature.
Right. If all of your causal geodesics reconverge, then your elementary light cones don't grow indefinitely. And that puts a bound on your curvature. Right?
Wait a minute. If look, we're saying that the delay in the resolution of a branch pair is what allows for curvature.
Yeah, we just said that.
Well, I'm just saying it again.
No, but you see my point about causal graphs, right? It's exactly the same story.
Yeah, I know. reflects curvature. Right. Because in the light cone, which is essentially the branch pair of a causal graph, you're saying that if we have a light cone and then we take the edges of the light cone and we see, do they converge again? That's a similar story to curvature. Yes, okay. All right. Okay, but so what? The curvature leads to the difficulty of theorem proving. So that's a fine statement. Okay, how is curvature? Okay, and a causal disconnection prevents theorems from being proved, basically. Prevents theorems from being true. I mean, from being proved across the event horizon.
Mm-hmm.
Okay, so what is the analog of energy here? The analog of energy is we can make, for any one of these things, we can make a causal graph, right? For one of these.
Mm-hmm.
But what is the significance of that causal graph?
Well, I mean, I'm gonna say the same thing I always say, and you're gonna object to it in the same way you always do.
I know, isn't it amazing that, the most remarkable thing is that just by repeating the same thing enough times, it eventually becomes
Right. But yeah, I think it's abstraction.
Yeah, okay, but let's take a look at that. Okay, so let's say, wait a minute, evolution causal graph here. Okay, so now we've got a causal graph. Now, how do we interpret this causal graph? Each one of these, so each edge is a lemma, but many of these are the same lemma, right? Many of these edges are the same lemma.
Mm-hmm.
So what does this causal graph mean?
Well, it's giving us an indication of every time a prior result was used in proving a future result. Right?
Prior result was depended on, not used, depended on. Because used would just be that lemma is used. Right? And this certainly doesn't connect every copy of a particular lemma. It connects only copies that were causally necessary to prove the next thing.
Right. You had to use that effect, as the initial condition to reach the next thing. So in the case where you separate rules of inference from axioms, it is exactly a graph of, what things were used in the proof of what other things.
Wait a minute. The thing we're doing here is we've got these elements and they simply entail other elements here. So
Yes.
Then what exactly are these?
So like I say, in the situation where you make a separation between the rules of inference and the axioms, the causal edges are precisely those cases in which you are using prior lemmas in order to prove subsequent lemmas.
Okay, well, I mean, using prior lemmas to prove subsequent lemmas. So let's just walk through that for 1 second. Okay, let's walk through that for a simpler case, just to understand what we're talking about here. I'm a little bit concerned about this. So let's take this case here. Okay. So what do we mean here? So we've got this result, A goes to AB goes to ABB. So in what sense is this lemma, AB goes to ABB, used to prove, so that what this is saying is, i.e., AB goes to ABB is used to prove ABB goes to AA. Now, why is that true? Why is that the case? I mean, this result, insofar as they're all coming from the beginning, from the Big Bang, that's true. But I don't think it's true.
Yeah, I mean, that's not the claim that I'm making, right?
Well, what is the claim you're making?
So you're still talking about the case in which you're treating the multi-way rules as being, ruleified axioms, and in which
Yes.
the propositions correspond to paths. So I'm saying in the case where you make a separation between the rules of inference and the axioms, this is the case.
So different case. Every state, every node is a proposition.
As a proposition, the rules are rules of inference, and the initial conditions are axioms.
Right.
Then when you have a causal edge, you're saying you couldn't have proved this new proposition unless this prior proposition had already been proved.
Okay, if every node is a proposition, then you're saying...
If every node is a proposition, then every event is a proof. Right.
Right. Every node is a proposition. So then every single event is a proof.
Yep.
As opposed to a path being a proof.
Right. And so then what you're saying is this event causally depends on that event. You're saying for this particular set of axioms and this particular set of rules of inference, this proof only works because this other proof, was done earlier.
Yes, I understand. Is a complete proof here. So that's a little weird because, for example, asking questions about undecidability become a little bit more obscure in this case.
Why? It's the same as in the other case.
Well, you're generating to get to a particular node.
What? Why isn't it the same?
You're getting from one proposition to another proposition through a bunch of steps.
Right. So in this case, anti-chains still correspond to undecidable propositions. Right.
Yeah, okay, fair enough.
AA can't be proved from ABBB in this instance.
Except it subsequently can be.
Okay, fine. But if that were a genuine anti-chain, then it would be the case. Undecidability works the same way as it does in the previous case.
Okay. Okay, so then every single event is a proof, but to prove a particular thing may take many steps with many nodes as lemmas, right?
Right.
So this case here is the more traditional theorem prover case, right?
Yes. Yeah. This is precisely what fine equational proof is doing.
And so now, do you have the code that puts equal signs inside here?
Yes, we have that in multi-way operator system.
How do you use it?
Uh, I believe, hang on, I'm pretty sure I sent it to you.
Well, where's the,
That was the thing that this morning you sent me an email saying, did this get integrated? And I wasn't entirely sure what that meant.
I'm probably confused too. Hold on a second. Okay, so this is, so where is multi-way operator system? Is it in here?
In that equational multiway.nb thing, there is a version of equational multiway system contained in that notebook.
Okay, but in here, is there something or not?
For the equational case?
Yeah, with equations.
Well, I mean, you can add your own equational axioms, but I have those equational axioms curated in that equational multiway notebook.
This equational multiway notebook.
No, I sent you a notebook called equational multiway that you then sent back to me today.
Oh God. Wait a minute. You sent that previous, could you resend it? Because I'm totally confused.
Sure.
And so you say that is equivalent but different from the equational multiway thing that I had.
I don't think it's equivalent because, yeah, this is why I don't like the naming of equational multiway system.
Okay,
right?
so you think this should be called two-way multiway system or something.
Or something, right? Equational multiway system, in my humble opinion, should be something where every multiway state is an equation, just like in find equational proof graphs.
Okay, fine. Why don't we call that multi-way equational system?
Yes, that's more consistent with our prior naming conventions. Yeah, okay, that makes sense.
Could this be called multi-way pair system, this two-way thing?
Could be. What is there a canonical name for bidirectional rules in Wolfram language?
Two-way rule.
Multi-way.
You're saying these aren't really equations.
Well, the rules are equations, but the states aren't, right? And
But you're saying that these things are really a two-way rule, aka like that.
right. So if you scroll down to the bottom, there are some examples there of equational systems.
Okay, so then to make this work, what I have to have this is basically a multi-way equational operator system, or multi-way equational.
Right. I mean, my plan was to have multi-way operator system in the function repository and have an equational layer on top of it.
Yes. Right. So so that would be multi-way equational system. Okay, so here, so let's see, where do you have, what's this?
That's Boolean algebra. It gets quite complicated after 3 steps.
Right, so in principle, I could use my, did I try this already? I could use my axiom for Boolean algebra, right?
Of course.
So let me just save this somewhere. I'm just trying to keep this organized. So let's see. Let's just go. I mean, this isn't just equational. This is what are we going to call this? This is metamath propositional. So your basic claim is that I can take any equational axiom system and you're going to turn it around so that it's got uniques in it and things, right?
Yep.
Whose
Your axiom system.
what's that?
That's your axiom system.
Okay, hold on, let me just. Okay, hold on, metamath, multiple. That's only one step, that's not too exciting. Wait a minute, what's this doing? What is this doing?
That's not doing the right thing. Are you definitely running the right code?
I just ran multi-way operator system.
From that notebook?
No.
Try running the code at the top.
And then let's figure out how to merge those. Well,
Yeah, there we go.
Different. Well, okay, so hold on. That. Oh dear. Okay, so what's the difference between that multi-way operator code and this multi-way operator code here?
Because I was working on this new multi-way operator code today, and I haven't merged it into the notebook.
Into which notebook? Into this one here?
No, into the function repository notebook.
Okay, should I just do it? I'll just copy this.
Okay, I'd rather be sure what I was doing, but okay.
I mean, is it the same code or is it not the same code? No, it might be the same.
No, I've modified it. It's obviously not the same code. It does a different thing. It should be merged, but
okay, all right. So if that's something you could, I know you need to go to sleep in a minute, but if that's something you could do, okay, so then this, okay, look, let's not untangle this mess here. I mean, what you're basically saying is that by giving the axioms of equality, where are those axioms?
In multi-way operator system for the equality case.
Oh, here we go.
It's just a commutativity axiom.
Is that all you need? You don't need some kind of transitivity axiom?
You do if you want to have implications, but we don't in this case. All you need is the axiom of paramodulation, which is basically just a commutativity rule.
Okay, so fine. So you can do this. God, I get so confused. Every time I think about this, I get confused. So yeah, okay. So what do you conclude from all of this? So okay, so we've got so now I'm buying that. There's a question. I mean, why do causal edges not just continue to accumulate? Because things will always depend on the past. Am I being silly about that? Oh, because we do only one level causal edges. Right? So the causal edges that are the flux of causal edges through a particular thing is just the most recent batch of things that got used. Okay, you need to go, but look, there are three things that are mixed up for me. Okay. There's the question of how many causal edges accumulate at a given point. Oh gosh, I don't understand this. Look, this is a theorem, a proposition implies another proposition. But that proposition might imply many different, there's no reason to think that there's only one proposition that it implies. I guess there isn't in this case, there are multiple propositions that it implies. What do you think? I mean, in the end, we're saying okay, so the claim is the difficulty of proofs is associated with the number of causal edges that are coming in. Right? That's the basic claim, that the difficulty of finding a proof. Is that right?
Well, that's the Einstein field equations. Yeah.
You say that so depends on the number of causal edges that come in, i.e., because that represents the number of branch pairs. Why? Why is that related to the number of branch pairs?
Well, because that's what the EFEs say, right?
I know that. Because, okay, so the difficulty, the number of causal edges, causal edge density leads to branch pairs. But just why in this situation? You have to take the continuum limit to get that result, don't you? Right, sure. That's the result.
But you're basically saying, look, causal edge density tells you how many prior results you can build upon to get new ones, right? And all you're saying is the more prior results you can use, the more different ways you can take a wrong turn.
Yes.
Like
Right. So I mean, roughly, the more prior is,
the
yeah,
more you know, the more wrong turns you can make.
right. If you know only one thing, you can do only one thing.
Right.
But how do we see this explicitly here? So every time we have a causal edge here, and we go down one more step. This is a branch pair here. How do we see that the presence of causal edges above it leads to the presence of that branch pair? Is that obvious? I think it's not terribly obvious, and I think it requires some limit.
Mm-hmm.
And that's saying that on the limit of a high density of a large number, if you go on with mathematics for long enough, this is what's going to happen. But to get the Einstein equations, there is some assumption about how, what does the dimension of this space tell you? Right, the dimension of the space, the geodesic balls in the space are basically telling you how many propositions can you get to within a certain length of proof from a given one. Right?
Mm-hmm.
It's the corollary ball of a given thing. What does the propagation of a corollary ball, which will be determined by curvature, what does that tell you? As the corollary ball propagates through the system, is parallel transported through the system, and gets bigger and smaller. So the more you know, the more that corollary ball should be crushed. Right? That ball that starts from a certain size here, those geodesics will converge as a result of these causal edges. That's the basic claim. Do you agree?
Yeah.
You're not paying attention. You're off.
No, increased curvature causes conversions of geodesics.
I know that, but what is the significance of right? So causal edges cause the contraction of corollary balls. And the claim that you made at one point was that eventually leads to singularities, as in the corollary ball eventually compresses to nothing.
Yes. If curvature is allowed to grow without bound, that's what will happen.
Right. And but what's happening is the curvature, if the curvature grows, the number of branch pairs, the branch pair density increases. And what happens to the corollary ball as it comes through this area of increased branch pair density? I don't understand that, because it seems like when there are more branch pairs, does that lead the corollary ball to compress to nothing. Right, so if we have a larger number, what we've started off with is we've got a bunch of initial conditions here. And the question is, do those initial conditions, i.e., do a given set of initial conditions all converge to the same thing? Well, anyway, it sounds like you were tired, and I'm sorry I kept you up late.
No.
Well, I mean, any great conclusion from this? I mean, the issue is, so what is the conclusion for mathematics from all of this? That's my question. I mean, we had come up with a claim previously, which I'm not sure I believe. And the claim about, I think as soon as if you're on a path, and you're always making one step from what you had before, it's sort of inevitable that you can prove things. If you just say, I'm going to pick a random hypothesis, there's no reason to think that there's a path from where you are, from what you've already proved to that hypothesis. I mean, that's more of the experimental math story, to my mind. But just for 1 second, the continuum limit of mathematics, what do we learn from it? We learn that in places where we know a lot, okay, the claim would be in places where we know little, where there are few theorems that build up, that it is easier to prove things. But, it's a little confusing because there's metamath as it gets laid out itself, and there's metamath as humans explore it, so to speak. So as humans add more lemmas, the structure of the space changes, which is a little different from the case of physics, except in your completion interpretation, where again, the structure of the space changes.
Right.
But what's the significance of your completion approach for this? I mean, what's the significance of that? I mean, what does it, I'm just trying to understand if we project the infinite future of mathematics, right? The infinite future of the universe is a bunch of black holes. Is the infinite future of mathematics similarly a bunch of black holes? I mean, it partly depends on the overall expansion rate. Anyway, you need to go. I'm sorry to keep you up so late. To be continued.
That's okay.
All right. See ya.
No, sorry. Yeah, just before I go, I mean, okay? What should I currently be prioritizing? Because right now I've been mostly focusing. Well, I've been focusing slightly on catching up with various academic responsibilities that I've let fall by the wayside, but also on trying to get things published from the summer school.
Yes.
But I don't know if that's...
Wait, like what? Like what?
So, I mean, so like this paper that, or this couple of papers that Xerxes and I are going to be writing, so we've now, or at least I have a draft of the kind of more philosophical one, and I'm working on writing the more technical one.
What's it called? What's that one called?
The more philosophical one?
Yeah.
It has the same title as the bulletin.
Okay.
Foundation for Mathematics and Physics. The more technical one, I don't know yet.